Hello, my name is Roberto Calandra, and today I'll be talking about our work on building an ecosystem for research on touch sensing. The main motivation for our work is the fact that touch sensing is a crucial sensor modality both in humans and in robots. And part of the reason is that touch is the primary sense that allows us to measure forces and contact with the environment. And therefore, if we really want to be able to control the environment and interact with it efficiently, we need to be able to measure these forces that we are applying to the world around us. And this fact is exemplified by experiments performed by Ronald Johansson at the University of Umeå, where they would anesthetize their sense of touch of humans while maintaining their motor control capabilities. And what we would observe is that humans would suddenly have much more difficulties in manipulating objects, like in these videos where it suddenly takes 3-4 times longer in order to light a simple match. And part of the problem about touch sensing is that it's a very hard field, and it's a hard field for a number of reasons. One of the first reasons is that this is an intrinsically interdisciplinary field which require integration between different components, from the hardware design to the actual processing of these raw measurements, from the robot control to actually using touch sensing into real-world applications. And in practice, over the past decades, we've seen that a lot of the applications and solutions found in touch sensing have been very ad hoc, where research would be used for a very limited number of works, but would not be reusable or extended to the larger community. And therefore, as a result, for new researchers and practitioners to enter the field, there is a very high entrance bar where they need to be able to independently develop hardware, processing, and control and applications. So in this talk, we will try to answer some questions of how can we lower the entrance bar for new researchers and practitioners, how can we improve reproducibility in the field, and how can we accelerate research by reusing existing components. And in order to answer these questions, the common thread that you will see during the whole talk is that we have been working very hard in order to standardize touch sensing and to create an ecosystem of tools and models that can be used and applied by the whole touch sensing and robotic community. And really, the fundamental questions that we would like to try to answer is how can we fill this gap between the principle of applying touch sensing to an application and the actual applications? What are the components that we need in order to make touch sensing practical and useful in real-world applications? And our answer to this question will be represented as 4 fundamental pillars that we believe are important. And these pillars will be hardware, simulation, touch processing, and benchmark and datasets. So starting from hardware, the problem with touch sensing hardware is that it's difficult to actually acquire hardware, and there is not much hardware available. And in 2020, we open source the first low-cost, compact, high-resolution tactile sensor, which was compact enough to be mounted on robot hands. And Digit was designed from the beginning to be easy to manufacture, to be reliable, and to provide high-resolution imaging through the use of vision-based tactile sensing technology. And here you can see some of the images that Digit would return when in contact with different objects. And the tactile sensing measurements that we would observe provided with a resolution down to about 15 micron, and quite remarkable sensitivity to the geometry of the object that we are touching. And if we compare Digit to leading commercial products like the Biotech, which is commercially available, both of them can be mounted on multi-finger hands. However, while Biotech has 29 contact points, Digit can measure up to 300,000 contact points, which is 3 orders of magnitude higher resolution. Moreover, while Biotech costs around $15,000, manufacturing a Digit in batch of 1,000 units costs about $15, which is again 3 orders of magnitude cheaper to manufacture. Finally, Digit is open source, and everybody with minimal mechanical and electronical experience can actually manufacture one in their own workshop. And again, all the components to are open source, so by going at digit.ml, you can find everything you need to build one. And so far, we've seen that Digit has been replicated in over 15 universities, which is a great confirmation of our work. Yet, for people that are not expert with mechanical or electrical manufacturing, it can still be challenging to produce a sensor. And to address these issues, we are very excited to announce that we have been partnering with GelSat Inc., and they will be commercializing Digit for the whole touch sensing, robotic, and machine learning community in order to enable even easier access to high-quality touch sensing hardware. The second component after hardware is simulation. Simulation is a very important tool in the toolbox of every researcher, and simulators play really a crucial role in prototyping, debugging, and benchmark new advances in robotics. However, while most rigid body dynamics engines include some form of traditional tactile sensor measurements, for example, capacitive or resistive technologies, those are typically low dimensional inputs. And the more contact points you want to evaluate, the more the simulators typically become slower. As such, simulating thousands or hundreds of thousands of contact points that a vision-based tactile sensor such as Digit can provide is typically impractical with common simulators. For this reason, we open sourced in 2020 a simulator, a fast simulator called Tacto, that is designed intentionally with the idea that we want to be able to simulate vision-based tactile sensors with hundreds of thousands of contact points very fast and very accurately. And some of the main features of this simulator is that it's extremely fast, can be used on GPUs at over 100 frames per second. It's general purpose in the sense that can be integrated with different physics engines and can simulate different vision-based tactile sensors hardware. It's physically accurate in the sense that it doesn't it relies on the your physics engines of choice, and therefore by choosing which particular physics engine you want to use, you can integrate it with it. And at the moment it makes use of rigid body dynamics, but can in theory be used also with flexible simulators. Finally, and this was very crucial for our work, it provides very accurate rendering, where it can simulate the soft deformation of the elastomer when applied increasing forces, and can be calibrated to simulate real sensors such as Digit. And finally, it's open source, and therefore anybody in the community can contribute and improve it. The overall software architecture of Tacto is that under the hood uses PyRender in order to simulate different sensors that are provided as separate file configurations. And as such, it can simulate sensors like Digit, it can simulate sensors like OmniTac and others. And the Tacto simulator can be integrated into any physics simulator of your choice, for example, PyBullet or Mujogo. And here we show some example of the rendering from a simulated digit on top compared to a real sensor measurement from the real sensor at the bottom. And you can see that qualitatively our simulator can approximate very nicely the measurement from the real sensor. After hardware and simulation, the third pillar of our ecosystem is touch processing. And here I would like to draw a comparison with some historical past. The introduction of the telephone and the widespread introduction of devices capable of recording audios in the end of the 19th century has produced a lot of interesting fields of research, like signal processing, and the corresponding machine learning community dedicated to better understanding and processing audio. At the same time, in the same way, the introduction of cheap, reliable hardware for vision cameras that happened at the end of the 1990s has created and very strongly accelerated the corresponding field of computational science, such as computer vision, which have been extremely successful, but rely on the presence of this reliable and cheap hardware that anybody can use. Similarly, it's our belief that we are now at the verge of the historical moment where tactile sensing hardware will be sufficiently reliable, cheap, and widespread that we are gonna be creating a new field of computational science dedicated to touch, to better understanding touch and better understanding what are the models for processing such measurements. As such, one of our goals is really the creation of a new science of touch processing. And this science has currently very limited literature about what are the computational needs in order to process touch sensing, and has many open questions that we hope in the next decades researchers will work on and will help us to understand, such as what are good features for touch, what is even the representation that we need from the hardware sensors, and what are useful structure in computational modeling for touch. For example, what would be the equivalent of a convolutional neural network for touch. And as a first step toward the creation and the widespread adoption of this new field, we open sourced and published in 2021 PyTouch, which is the first machine learning library explicitly dedicated to touch processing. And the idea here is that we would like PyTouch to become the equivalent of an OpenCV for touch sensing, where anybody can use this library to process data even without being an expert in the field of machine learning. And some of the important features of PyTouch is that it's based on PyTorch, and it's the first machine learning library dedicated to touch processing. It's hardware agnostic by providing several abstractions for using different types of sensors and for rapid experimentation. It's also a platform that provides standardized evaluations and comparisons of different models. So if you want to develop a new models, it's easy to compare and evaluate against existing models. And finally, it provides pre-trained models as a service where even non-machine learning experts can just download pre-trained models and use them into their applications without having to learn or becoming expert in the machine learning field. And this is very valuable, and it can also be used for fast fine-tuning to new applications. Finally, PyTouch provides native integration with Digit, so with real-world hardware, as well as Tacto, so simulators. And we're working on adding support for non-vision-based tactile sensors. And again, this project is open source, so if you are interested and want to contribute, you are very welcome in this effort. Here, there is an example of PyTouch code. And here you can see how in about 10 lines, you can essentially connect a real-world tactile sensor, like a Digit, to a machine learning, a pre-trained model that will be detecting if there is a contact or not. And all of this is very simple to use, and you don't need to be an expert again, neither in hardware nor in machine learning. The fourth and final pillar of our ecosystem after hardware, simulation, and touch processing are benchmark and datasets. Benchmarks are, again, a crucial aspect for any scientific community, since having benchmark allows the community to really measure in an objective way what are the advances that have been done. And we believe that it's now the time to think very carefully about what are the benchmarks that we will want to have for touch sensing. And in particular, we believe that there are two main enablers for starting this discussion. The first enabler is the fact that we are now at the point where we have accurate touch sensing simulators that can be used by people that do not have hardware access. And on the second hand, we have standardized hardware which is easily available to the scientific community, such as Digit. And therefore, again, we have the possibility to reach a wider audience, and therefore we need to be able to better measure what are these metrics. The second aspect is datasets. So far, there have been very few touch sensing datasets publicly available. And we believe that this was largely caused by the limited availability of existing hardware. So we hope and we want to encourage the scientific community in the future with larger availability of simulators and hardware to start creating new and larger datasets. And in order to do this, we also need to accept as a community that this is a valuable enterprise that needs to be better acknowledged. As a first step toward creating better and larger datasets, through our simulator Tacto, we collected a dataset of over 1 million grasp on a simulated object, and we here show how on these large datasets we can compare what are the performance of different sensor modalities used for learning grasp stability. And in this case, the results seem to indicate that using vision and touch outperform models that are exclusively making use of vision or exclusively making use of touch. Finally, after we have all of these four pillars, we are also able and interested in working on real-world applications that make use of touch sensing. Some of our recent work on these fields have been work that we have here at NeurIPS 2021 on active 3D shape reconstruction from vision and touch. where the basic idea is that we want to be able to integrate the global informations that are provided by vision as a sensor modality with the high resolution but very localized informations that touch provides in the moment when you actually enter in contact with an object. And in order to do so, we use a reconstruction network, but at the same time, we also want to be able to learn a policy that is able to decide in which part of the object we want to touch it at the next time in order to improve the reconstruction quality of the object. A second work that we recently published on arXiv is a work where we are interested in learning to play piano by using tactile sensors in order to effectively better control the keys that we are pressing, better control the forces, and ultimately producing music which is accurate and that sounds in the same way that a music score would. And here there is a small example of the hand playing on the piano. Finally, after having talked also about application, something that we've been very actively working on is the meta level of community building. We believe that community is a really important aspect of any research field, and we are interested and keen on growing and fostering a community around touch sensing, touch processing, and the development of tactile sensing hardware. As such, we have created a Slack channel where we invite all the people that are interested to join. This is absolutely free. And if you're interested, please go to touchsensing.org and join this community. To conclude, all of this work would have not been possible without the contribution from dozens of collaborators that have been amazing, and I am humbled and honored of having worked with all of them. But in particular, I want to call out here the contribution of Mike Lambetta, who has been leading many of these efforts, and especially the design of the digit sensor. To conclude, in the talk of today, I hope that I've convinced you that touch is a key sensor modality in both humans and robots. And over the last few years, we've been dedicated to this large goal of creating an ecosystem that allows to simplify the integration of touch sensing in real-world applications, and that really enable robots to perceive, understand, and interact through touch. As a part of this ecosystem, we've been working and developing hardware, we've been developing simulations, touch processing libraries, and we've also given quite a bit of thought on benchmark and datasets, as well as real-world applications. We want to grow and support the community around touch sensing, and for this reason, the large majority of our work is open source, and it's easy to reproduce, and we want to continue to foster this reproducibility. Finally, our long-term goal is making touch sensing practical and more accessible, both for researchers and in the real-world applications. Thank you for your time.